All right, in this video we're going to talk about section 13.7 from your textbook, which is about a topic called differential equations. So before we get started, notice a differential equation is just going to be an equation that involves a derivative, hence the word differential, right? That's sort of what makes an equation a differential equation. And I should mention that differential equations represents a really big field of study, right? So this is not the whole enchilada, if you will. Section 13.7 is just barely dipping your toe in the water. But, even at Midland College, we have a course on differential equations, and if you went to a university, you'd be able to find many more courses over differential equations. So if this topic interests you, there's a whole lot more to study in this direction. But today we're only going to discuss the easiest, very most simple kind of differential equations. And if you were to talk to a mathematician, you would say that you have studied separable, ordinary differential equations. That's the type of equation we're talking about today. So look at example 1. Jane is running in a 3-mile race. Her velocity in miles per hour changes over the course of the race, according to this formula. So it looks like she starts out when t is equal to 0, she starts out at 8 miles per hour, and then over time it looks like her velocity will decrease by 4 miles per hour. And that sort of makes sense, right? As you run longer and longer, you tend to get tired and you slow down. And so this seems like a reasonable formula here. So lowercase t represents time in hours. First, we want to find a formula that gives us her distance, like her distance away from the starting line as a function of time. And then after we have that formula, then we would be able to figure out how long it's going to take Jane to complete the 3-mile race if her velocity really does follow this formula. So the first thing we need to do is recognize that velocity is really just the rate of change of your distance over time. I'll repeat that because it's important. Velocity is the rate of change of your distance over time. So how quickly is your distance changing over time? If your distance is changing very rapidly over time, that means you have a high velocity. If your distance is changing very slowly over time, that means you have a very small velocity. And you know that the derivative can be interpreted as a rate of change. And so we could write the velocity is equal to the rate of change in the position or the distance over time. So I'm using p for distance. And so I would write the velocity as dp dt, because dp dt in symbols is talking about the ratio of the change in distance divided by a change in time. Okay. So knowing this, I can rewrite that differential equation by this. So v equals 8 minus 4t. I can write dp dt equals 8 minus 4t. And now it becomes obvious to us that this is a differential equation because I have a derivative in the equation. Now, I want a formula that gives me the distance p, and my p here appears inside the derivative. So I'm taking the derivative with respect to time of p on the left side. On the right side, I have 8 minus 4t. But if I want to undo this derivative, if I don't want that derivative to be there, I really just want to get to that p by itself, what I should do is I should take the antiderivative then with respect to time, and that antiderivative will undo the derivative with respect to time. But if I do that to the left side of my equation, I have to do the same thing to the right side of my equation, meaning I have to take the antiderivative with respect to time of the right side as well. So on the left side, the derivative and the antiderivative will cancel, and it will just give me a p. And on the right side of the equation, I have the antiderivative of 8 minus 4t. Well, that's going to be 8t minus 4 over 2t squared plus c. When we're taking antiderivatives, we need that plus c constant. 4 over 2 is just 2. And so now I have a function where my distance p is a function of time. Now that's pretty neat, but what is the c value? Well, in order to figure out what is the c value, I should remember something. I need to remember that my race is going to start when time is equal to 0. And at time is equal to 0 at the start of the race, that would mean that my distance from the starting line is also 0, because you should be at the starting line at the start of the race. So if I plug in t is equal to 0 and p is equal to 0 into my solution here, I'll have 0 equals 8 times 0 minus 2 times 0 squared plus c. And so that tells me that c has to be 0. So if c is 0, I can again simplify this formula. It gives me my distance as a function of time as just 8t minus 2t squared. And this would be your answer to the first part of my question, where I ask you to give me a formula for distance as a function of time. Now I'm going to switch pen colors to work on the second part of the question, so that you can tell the difference between my work here. But we want to find now how long it takes for Jane to complete the 3-mile race. And so basically, whenever I let p equals 8t minus 2t squared, and I want the distance from the start of the race to be 3, because I'm running a 3-mile race, what time t corresponds to a distance of 3? Well, I just have to plug in 3 in for p and now solve for t. So I need to rearrange this just a little bit. I'll add 2t squared to both sides. I'll subtract 8t from both sides. And then that will leave my right side of my equation as 0. Now you recognize this as a quadratic equation, which you learned how to solve in algebra class. For our purposes here, I'm just going to use the quadratic equation. And so the quadratic equation tells me that my solutions are going to be negative b over 2a plus or minus the square root of b squared minus 4ac, all divided by 2a. And here, notice my a coefficient is 2 in this quadratic, b will be negative 8, and c is going to be 3. Which means that my solutions are going to be negative 8, which I call positive 8, divided by 2a, so b divided by 4, plus or minus the square root of b squared, which is 64, minus 4ac, which is going to be 4 times 2 times 3, which would be 24, all divided by 2a, which is 4. So in the end, 64 minus 24 is 40, so I'm talking about square root 40 over 4. Square root of 40 is like 2 square root 10, and so I could write this as square root 10 over 2. And that means my two solutions to this quadratic equation would be 2 plus square root 10 over 2 and 2 minus square root 10 over 2. Now, let's think about this just a little bit. You know, she's starting off the race running 8 miles per hour. And after 1 hour passes, her velocity would be 8 minus 4. So she ends the first hour by running 4 miles per hour. So during that first hour, she's going to run somewhere between 8 miles and 4 miles, both of which are greater than 3 miles. So we're sure that she's going to finish the race in less than an hour. We know that just by looking at the velocity equation and the length of the race. And so I know that my time t has to be somewhere between 0 and 1. So my solution definitely cannot be 2 plus root 10 over 2, because 2 plus root 10 over 2 would be more than 2 hours. So then my solution has to be 2 minus root 10 over 2. And I don't have a calculator on me, but, well, I mean I do, but you wouldn't be able to see it. So I'll use Desmos, and maybe you can't see this either, but if I do 2 minus the square root of 10 divided by 2, Desmos tells me this is 0.42. So this is t equals 0.42. So a little bit less than half an hour. And if I wanted to find that out in minutes, what I could do is multiply that whole thing, or I should say, I should divide the whole thing. No, I was right the first time. I need to multiply the whole thing times 60, because there's 60 minutes in an hour. And this tells me that this is going to be 25.1 minutes. So that's how long it takes Jane to finish her 3-mile race. Okay, so that would be part 2. And so in example 1, maybe this isn't too unfamiliar to you, but you've just solved your first separable ordinary differential equation. Okay, so let's take a look at example 2 now. Example 2 says John is also running a 3-mile race. His velocity in miles per hour changes over the course of the race as well. So my formula now tells me that his velocity starts off at 7 miles per hour, and then his velocity will decrease by 1 mile per hour for every mile he runs. So after running 1 mile, his velocity will be 6 miles an hour. After running 2 miles, his velocity will be 5 miles an hour, and so on, according to this formula. Just like before, we remember that velocity is just the rate of change of distance over time. So we can write it like a derivative like this. And in our case, we write derivative equals, and using my formula, the right side would be 7 minus p. Now, if we were to use the same methodology we did last time, and we said, well, the left side of my equation is the derivative with respect to time of p, so let me take the antiderivative with respect to t in order to undo the derivative. Well, then I would have to do the same thing to the right side of my equation. And so, of course, the antiderivative of 7 with respect to t would be 7t. But what's the antiderivative of p with respect to t? Well, we know p, our distance, is a function of time. And so it's not just going to be pt, that's what it would be for a constant, but instead we need to know what function of time it is. But remember, what are we trying to do right now? Well, right now we're trying to find the formula that describes distance as a function of time. So we're not going to be able to do this part. This is just not possible to us because in order to take that antiderivative, it would presuppose that we already know what we're trying to find. So anyways, let's rewind a little bit and see if we have a different approach here. What I'm going to do instead is I'm going to divide both sides by 7 minus p. Okay? So then the left side of my equation becomes 1 divided by 7 minus p times dp dt. And the right side of my equation, 7 minus p divided by 7 minus p, would be 1. Give myself a little bit more room here, because after making that change, now I'm going to attempt to take the antiderivative of the left side with respect to t and the antiderivative of the right side with respect to t. On the left side, we notice that I have a dt in the numerator and a dt in the denominator. And you are actually allowed to cancel these dt's so that on the left side now, it is just as it appears. We're taking the antiderivative of 1 divided by 7 minus p with respect to p. Now, let's quickly do a u substitution on the left side then. And so my u sub is going to be setting u is equal to 7 minus p, meaning that du dp is going to be -1. And that means that my dp can be replaced by negative du. Okay, and then my new left side of the equation becomes negative antiderivative of 1 over u du. And on the right side of my equation, the antiderivative of 1 with respect to t is just going to be t, and I'll also throw in a plus c since I'm taking an antiderivative. Okay. Now on the left side of my equation, the antiderivative of 1 over u is going to be natural log of u. And I could add a plus c over here, but if I call this one c1 and that one c2, what I could do is just subtract c2 from both sides, and then I end up getting natural log of u equals t plus c1 minus c2. But at this point, we haven't decided yet what value c1 has and what value c2 has. The word we use to describe these is arbitrary. c1 is an arbitrary constant, c2 is an arbitrary constant. And so whenever I add or subtract two arbitrary constants, what I end up with is also just a constant. And also, depending on my freedom of choice for c1 and c2, that sum or difference also is just arbitrary. And so I will just call this plus c again, because again, depending on my choice of c, I can account for my choice of either c1 or c2. Hopefully that makes sense. I can't think of an easier way to describe that. Now, what I really want was p and not u. I don't really care about that lowercase u. So I take negative natural log and then I replace the u with 7 minus p. To get rid of the negative on the left side, I have to multiply both sides by a negative, so this would be natural log of 7 minus p equals negative t minus c. And just for the same reason, since I haven't decided on whether my c value is going to be positive or negative, it's still up in the air, it's still arbitrary, I could just make that negative into a positive and it won't really change anything. To undo a natural logarithm, which is just the logarithm with base e, I'm going to employ the exponential function base e. So I'll compose each side of the equation with my exponential function base e, and I'm going to find 7 minus p is equal to e to the power negative t plus c, like this. And now, again, let's remember a little bit of properties of exponents here. Whenever you're adding two things in the exponent, you can actually just multiply two exponential functions with the same base. So instead of having e to the power negative t plus c, that's actually equivalent to e to the power negative t times e to the power c. By the way, one easy way to think about this, if you weren't convinced, is that if I have x squared times x to the third power, well, that would be x times x for x squared times x times x times x for x cubed. And notice this is, multiplication. Multiplication is associative, or yeah, that's right. Multiplication is associative. It's a correct word. So this is just 5 x's. I can get rid of the parentheses, and this is x to the 5th. But what is x to the 5th? Well, 5 is just 2 plus 3. So you can see that x squared times x cubed is just x to the 5th power, x to the 2 plus 3. And I'm using the same logic over here whenever I tell you that e to the power negative t plus c is just e to the negative t times e to the c. Okay, now e to the power c. Let's think about that for a moment. So e to the power c is just a constant, 2.71828 and so on, raised to the power of just an arbitrary constant. And so that sort of puts a specific constraint on this thing. You know, and the exponential function always has to have a positive value for a real number input. But aside from being positive, this e to the c could be any positive number. Depending on my choice of c, I can make e to the c any positive number. And so I'm also just going to sort of transfigure that e to the c into just a c, where lowercase c still represents any arbitrary constant. So I want you to know that that is allowed as well. And so if I'm solving for p, p is then going to be 7 minus c times e to the power negative t. And now we have a formula that tells me my distance from the starting line as a function of time elapsed during the race. Now, what is my value for c? And by the way, whenever I have this formula and I start asking the question, what's the value of c? Now at this point in the problem, I can no longer say, oh, well, c is arbitrary, so I can make this negative into a positive or a positive into a negative, and I can't, continue to move around where it is with location to like a coefficient or an exponent and so on. All those sort of tricks where I've been a little bit, a little bit loose with where I put the c and how I deal with it. I can no longer do those once I start asking the question, what is c? Having asked the question, I have solidified c's role in this equation, and now I'm stuck with it. So, no more funny business. And what I have to do is realize that we're talking about a race here. And just like before, my initial value for time at the beginning of the race was 0. My initial value for p was 0. So if I use this formula and I set p equal to 0 and then 7 minus c times e to the power negative 0, well, that's e to the power 0. E to the power 0 is just 1, because anything to the power 0 is 1. So then I would have 0 equals 7 minus c, which tells me that c has to be 7. So going back and plugging that value for c in, I have p is equal to 7 minus 7 c times e to the negative t power. Oops. My bad. I already plugged in 7 for c, so I don't need another c. 7 minus 7 e to the negative t power. Great. So I have an equation that tells me my distance as a function of time for my racer John in example 2. That was the first step. My second step, which I'll write in purple, is find how long it takes John to complete a 3-mile race. And so at the end of the race, my distance is 3, and I want to know what time corresponds to, a distance of 3. Well, notice I can factor out a 7 and get something like this. So 3/7 is equal to 1 minus e to the negative t, which means that e to the negative t is equal to 1 minus 3 over 7. 1 minus 3 over 7 would be 4 over 7. And to cancel out that exponent base e, I'll take the natural logarithm of both sides. And so taking the natural log of 4/7 is then going to give me negative t. And so we could say that t is equal to negative natural log of 4 divided by 7. And again, you would have a calculator. You would have specifically a TI-30 on your exam. And so you can actually evaluate a natural logarithm. But typing in negative natural log of 4 over 7 gives me a time of 0.56 hours Or if I wanted to make that in minutes, of course I multiply times 60 like I've done before, and that is going to be 33.6 minutes. And that's how long it takes John to finish his 3-mile race when his velocity is given by this formula, 7 minus the number of miles he's run. Okay. And so this gives us a way, notice in our example 1, velocity was given as a function of time. In example 2, velocity is given as a function of distance. And so be aware, just be aware, especially of these first steps. What did we have to do differently when velocity was a function of distance, right? Here's example 3. This says, crawfish is an invasive species to the Midwest region of the United States, which means that crawfish wasn't there natively, but humans have basically carried crawfish to the Midwest region and put them in the ecosystem. And now that crawfish are introduced, they're killing off a lot of the native wildlife. That's what it means to be an invasive species. So let's say that someone brought a cooler of 10 crawfish and illegally dumped them into a lake in the Midwest on a day that corresponds to t is equal to 0. And let's say that t is going to represent time in days here. We're going to develop a formula that predicts the number of crawfish in the Midwest on any day after you dumped the crawfish into the lake, right? Well, here's what I know about crawfish, and it's not very much. But what I know about crawfish is that if you want to make more crawfish, you have to have a male and a female crawfish mate. Now, males and females come in roughly 50% each of the crawfish population. So the larger the crawfish population, the more pairs of crawfish are mating and producing more crawfish. So that means the rate at which the number of crawfish changes with respect to time, that is proportional to the number of crawfish. If you have 1,000 crawfish, they will be mating and producing more crawfish at a faster rate than if you just had 10 crawfish, right? So I say the rate of change is proportional to the number of crawfish, and this is how I would write that statement in mathematical symbols. So my equation is dn dt is equal to k times n, where k is just some constant of proportionality. Again, k is a constant. I don't know what it is because I don't know how quickly a new baby crawfish grows up and matures and finds a mate and starts producing new crawfish. So k would depend on how quickly the crawfish are mating. But without knowing that, I just know that it's a constant, and we call that the constant of proportionality when we say that the rate is proportional to the number of crawfish. But this is just a differential equation, and I can solve it in a similar method of the way I did before. So I'll divide both sides by n, and I have 1 over n times dn dt is equal to k. And then on the left side of the equation, to get rid of that derivative with respect to t, I'll take the antiderivative with respect to t. And I want you to notice it was important here that I first divided both sides by n, because otherwise this wouldn't really work. You can try it yourself. I have a dt in the numerator and a dt in the denominator, so those cancel. And on the left side, that tells me that I have taken the antiderivative now of 1 over n with respect to n, which is natural log of n. And I could write plus c here. We'll call that plus c1. And on the right side, I'm taking the antiderivative of a constant with respect to t, so that's going to be a constant times t plus c. Now, just like before, I can subtract c1 from both sides, and whenever I have c2 minus c1, I'll just call that the arbitrary constant c, and remember that's just as good. Now, to undo the natural logarithm, or the logarithm with base e, I'm going to take the exponent with base e, decomposed with both sides of my equation, and just like before, I can bring down that c, since it's just an arbitrary constant, and I'll write as n equals c times e to the power kt. So what is my c constant? Well, I remember that whenever the day was represented by t is equal to 0, the day we dumped in the crawfish, n was equal to 10, because my cooler had 10 crawfish when I illegally dumped it into the lake. By the way, this is a hypothetical scenario. I'm not admitting to any felonies. I'm personally not a fan of crawfish, and I would not do any eco-terrorism. This is the purpose. The purpose of this is for a math problem, just in case the FBI is watching this. Okay, so n is equal to 10 on that first day. I have c times e to the power k times, and remember t is equal to 0 on that first day. So e to the power 0 is just 1, which tells me that c has to be 10 in this case. So now, rewinding back to here, I can write that the number of crawfish is equal to 10 times e to the power k times t, where t is the number of days that have passed, n is the number of crawfish now that are living in the Midwest region, and k is some constant that represents how quickly these crawfish multiply. And that was our goal, is to develop a formula that describes the number of crawfish in the Midwest as a function of time. And maybe it's nice to visualize some of these things, right? So I'll get on Desmos here and type in y is equal to 10 times e to the power k x. And so x is just a stand-in for t, y is just a stand-in for n because of the way that Desmos is. And what that means is whenever, time is 0, the number of crawfish is 10, but the number of crawfish really takes off in a dramatic way in a very short period of time. So let me make this a function, f of x, and if I were to evaluate, how many crawfish are there 30 days later, it's an enormous number of crawfish. And maybe that tells me that my k value isn't perfect, right? So if I'm going to let x represent the number of days, well, probably the crawfish population is not, it's not doubling every day. So k is not going to be 1, k is going to be something between 0 and 1. And if I lower that k, I'm saying that the crawfish are reproducing not as quickly, well then maybe my curve isn't quite so steep, right? Maybe it just looks like this, which would be a much better curve for an invasive species. And yet, as is the nature of all endangered species, even if they reproduce relatively slowly, like if I set the k value as 0.01 and make this slope as gentle as I can, man, after a certain number of days pass, you're still pretty much screwed in terms of that's a runaway crawfish population. It's getting bigger very rapidly after about 2 years. So in any case, that's example whatever, example 3. Here's example 4. It says, on a ranch in England, there are 10,000 cows. On a certain day, which we're going to represent by t is equal to 0, so t is going to be time in days, we find that one cow falls ill with an infectious disease. So n is going to be the number of sick cows. We want to develop a formula that predicts n as a function of t. Right, so if you tell me the number of days after the first cow got sick, I should be able to predict how many cows are sick on this farm. And so maybe your first guess here is that the rate at which cows are becoming sick, dn dt, is going to be proportional to the number of cows that are sick. And that would be mostly correct, right? So you imagine one person in a community is sick with a disease. Maybe in a given week they might spread it to like 2 other people, right? But if in a given community you have 100 sick people, and each of those people are spreading it to 2 other people during the week, well, then you've then gotten 200 new sick cases during the week. So it seems like the more sick individuals you have, the faster people in the community are becoming sick. So you would say this is actually probably a pretty good model, dn/dt. But that's forgetting one thing. It's actually, there's many, many more things you could think about and make this model very sophisticated. If you were someone who is working for the Centers for Disease Control, you would be developing a math model using differential equations, but also taking into account many, many different factors, including age and how, much people interact with each other, and are we using public transportation? Are we using masks indoors? What about vaccines? What about new virus variants? All of these things. But for our purpose, let's just consider one other consideration. That is, for new cows to become sick, you need an interaction between a sick cow and a healthy cow. Because you can't just have a cow that's sick creating sick cows, but you actually need healthy cows to become sick in order to have new cases. So this rate at which new healthy cows are becoming sick is not only proportional to the number of sick cows, but it's also going to be proportional to the number of healthy cows. Well, the number of healthy cows should be the total, 10,000, minus the number sick. And so this is going to be my actual differential equation that's going to more accurately model our situation, right? So this is the rate at which cows are becoming sick. And it's proportional not only to the number of sick cows, but also to the number of healthy cows. You can imagine this if you're still not bought in. What if, 9,000 cows are sick and only 1,000 are healthy? Well, then the number of healthy cows is actually the limiting case, right? You would basically be having a lot of interactions between 2 sick cows that wouldn't result in a new sickness because a sick cow can't get a sick cow sick. Okay, maybe I've talked that to death. Let's go ahead and solve this differential equation. I'm going to start off by dividing both sides by n times 10,000 minus n. So the left side becomes that times dn dt, and the right side of the equation becomes k. On the left side, I will take the antiderivative with respect to t so that I can cancel out those. And on the left side, I'll be taking an antiderivative of a function of just n with respect to n. On the right side of the equation, I'll be taking an antiderivative with respect to t, because I have to do the same thing to both sides of my equation, and the antiderivative of k with respect to t is just kt plus c. Now on the left side, if you want to take this antiderivative, it's going to require a technique called partial fraction decomposition. And hopefully you saw this in your algebra class or in your math for business class. If you haven't, that's okay. I don't think that I'll be including this on an exam or anything, but we're going to do it really quickly here to get to our interesting result. So using partial fraction decomposition, what I'm going to say is that my fraction 1 over n times 10,000 minus n is going to be equal to some a divided by n plus some b divided by 10,000 minus n. And I would prefer it in this form with the a over n plus b over 10,000 over n because I can actually take the antiderivative of the right side of this equation pretty easily. Now it's up to me to figure out what is a and what is b. Let me multiply both sides times the denominator on the left-hand side. So the left-hand side would then become 1. The right-hand side becomes a times 10,000 minus n, and then plus b times n. And this equation has to be true for any value of n, right? Anything like n equals 5,000, n is equal to 1, n is equal to 2. Even if n is equal to 0, this has to work. And so if I let n equal 0, my equation becomes 1 is equal to a times 10,000. And then what if I choose a different value for n? What if I let n is equal to 10,000? Well then, 1 is equal to b times 10,000. So it turns out a and b are both 1 divided by 10,000. Okay, so that's the entire method of partial fraction decomposition. That means that I can rewrite the left-hand side of my equation like this, the antiderivative of a divided by n, which would be, 1 over 10,000, antiderivative 1 over n, dn, plus the same thing b, which is also 1 over 10,000, antiderivative of 1 over 10,000 minus n, dn. So now these antiderivatives are not so bad on the left side. Like 1 over n dn is just natural log of n, so I have 1 over 10,000 times natural log of n. And then this antiderivative, if you use a quick u substitution where u is equal to 10,000 minus n, that means dn is equal to negative du. And so whenever I take that antiderivative, I'm going to have minus natural log of 10,000 minus n. Like so. Now on the left side, I'm going to use a property of logarithms that I know. If I'm subtracting two logarithms with the same base, I can actually just divide inside the logarithm. So this is going to be 1 over 10,000 times natural log now of n divided by 10,000 minus n. And if I multiply both sides times 10,000, I get the following. Same stuff equals 10,000 kt plus 10,000 c. But k is sort of an arbitrary constant of proportionality. And so 10,000 k, I could just choose a different value for k that's 10,000 times as large and just let k absorb that 10,000. And c is also an arbitrary constant. So when I multiply c by 10,000, it doesn't really matter. And so I can actually keep it simplified like this. And that's the best way I know how to explain that. I know it feels a little bit like voodoo, like we're doing something wrong. But if you keep in mind that k and c are arbitrary, and we haven't found those values yet, then we're okay. So then to get rid of the natural log, I take e to the power of both sides of my equation. And so the right-hand side is going to become c times e to the power kt. And now I want to solve for n still. I still don't have a formula explicitly for n. So we multiply both sides by 10,000 minus n times c e to the kt. And then I'll distribute the c e to the kt of 10,000 c e to the kt minus n c e to the kt. I can't actually make the c absorb the 10,000 anymore. And the reason for this is because I have another copy of that c over here. And so if I let the first copy absorb the 10,000, it would no longer be the same value as the c over here, but I want these to be the same value, and so I'm not going to mess with that right now. Maybe later, but at least for right now, I'm going to leave that alone. Now, what I'll do is I will factor out, I'm going to add nce to the kt to both sides. So this is n plus nce to the kt equals 10,000 ce to the kt. On the left side now I'll factor out the n, and I get n times 1 plus ce to the kt is equal to 10,000 ce to the kt. And I'm running out of room, so I'll go back up here. On the left side and the right side, I'll divide by 1 plus ce to the kt. I get n is equal to 10,000 times ce to the kt divided by 1 plus ce to the kt. And you could stop here. This is a good formula explicitly in terms of n. But a lot of times you might see people multiply both the top and bottom of this fraction by this. I'll show you what I'm about to do. And since I'm multiplying the top and bottom by the same thing, then it doesn't really change a whole lot. I'll multiply by 1 over c e to the negative kt, and then again 1 over c times e to the negative kt. So my new formula will be n is equal to 10,000 times, and then c over c is 1, and then the e to the kt times e to the negative kt is 1, so my numerator becomes 1. And then my denominator is going to be 1 over c times e to the negative kt plus 1. Right? And writing this just one more time, I know we've rewritten this like 1,000 times already, but I can rewrite this as 10,000 then divided by 1 plus c e to the power kt, where I let c be 1 over c from before, and again, since c is arbitrary, 1 over c is arbitrary, I can just transfigure that a little bit. And then I'll let that k absorb the negative, because again, k is just some arbitrary constant. And so this would probably be the most simplified way of writing a formula for n as a function of t. But I haven't really found what is c yet. And remember that on day t is equal to 0, we had just one cow sick, so n was equal to 1. So let me use this formula here. I'm going to take over here where I have more room to do this. But for n, I'm going to plug in 1, and for t, I'm going to plug in 0. So 1 is equal to 10,000 divided by 1 plus c times e to the k times 0. Well, e to the k times 0 is e to the 0 power. Anything to the 0 power is 1. So this is 10,000 divided by 1 plus c. So if I want to know what is c, I have to multiply both sides times 1 plus c. We find that c is equal to 9,999. So if I rewrite this one more time, I've said one more time quite a few times now, but here's 1 plus 9,999 e to the kt. Where the only thing I don't know yet is k, and k would be a constant that corresponds to how quickly the disease spreads through the population. So if the disease is spreading really quickly, k will have a different value than if c is spreading really slowly. And so you know that different viruses, different infections, different illnesses spread at different rates. Some are more infectious than others, and so k will have a different value depending on what type of infection we're talking about. So let me show you in Desmos what this looks like if I plug in this formula. I'm going to use y instead of n here. So I set y is equal to 10,000 divided by 1 plus 9,999 times e to the power kt. And I have a feeling here that k is going to be best off negative, so let's try that. And I would be right. So look and see what's happening here. What's happening here is, and I think it would be best if I rescale my x-axis. So I'm going to let x start at 0 and end up at, let's say, the end of the year, like 365. Whereas my y-axis can still be, oh, that wasn't enough time apparently. Huh. Well, maybe, let me change my, there we go, much better. Okay, so remember this red curve is now representing the number of cows that are sick out of 10,000. So this horizontal line up here, this is representing the number 10,000, right? This black dotted line is 10,000 cows. And so on day 1, or day 0, only 1 cow is sick. So it would be very, very small. We have to zoom way in to day 0 to find that 1 cow is sick on day 0. Now, as the illness spreads through the ranch, more and more cows are going to become sick. And it's going to look pretty much like exponential growth here, in that the number of new cases is going to be proportional to the number of sick cows, or at least roughly so, up until about half the cows are sick. And then in this last little bit of the regime, the number of new cases is actually closer to being proportional to the number of healthy cows. And so that's why it slows down as we approach 10,000 cows. And, we basically reach 10,000 cows and then we stop, because there's not more than 10,000 cows on the ranch. So this is a pretty decent model. If I allow k to be a larger negative number, or a negative number with a larger absolute value, that corresponds to the disease spreading faster. And so you see 10,000 cows get sick faster when k is a larger negative number. And if k is a smaller negative number, that corresponds to a disease that spreads more slowly through the range. Okay. That was example 4. Here's example 5. And I'm done with word problems. We're just going to do nice, easy, plain old math problems here. So what I'll do here to solve this is I'm going to multiply both sides by 7y minus 1. Okay. So on the left side, I have 7y minus 1 times dy dx. And on the right side, I'll have x squared plus 3. Because I want to get rid of that derivative and I want to solve for just y as a function of x, I'm going to take the antiderivative with respect to x of both sides. And on the left side, these dx's are going to cancel. And it turns out I'll be taking the antiderivative with respect to y, which is going to be 7 halves y squared minus y. And on the right side, the antiderivative with respect to x gives me 1/3 x cubed plus 3x plus c. Now I'm actually just going to leave this the way it is. And when we ask the question, what is c, we remember this, that y is 4 when x is equal to 2. So let me just plug in 4 here. And 2 on this side for x. And then we'll solve for c. So 4 squared is 16. 16 over 2 is 8. 8 times 7 is 56. 56 minus 4 would be 52. On the right side, 2 cubed is 8. So we're looking at 8/3 plus 6 plus c. So then I'll subtract 8/3 from both sides and subtract 6 from both sides. 52 minus 6 would be 46. And 46 minus 8/3 helps me think about this as 2 plus 2/3. So it would be 44 minus 2/3, so it should be 43 and 1/3. That's going to be my value for c. Okay, so then plugging in this value for c, I get 7/2 y squared minus y equals 1/3 x cubed plus 3x plus 43 plus 1/3. So let's just visualize this in Desmos really quick. You'll notice I didn't explicitly solve for y. I had a feeling, based on looking at that answer in blue here, the last line in blue, I had a feeling that that wasn't going to solve neatly as a function explicitly in terms of y. You can try it yourself if you want to, but I'm not going to waste time in this video. That's already getting pretty long. And so what we're going to have, if I put this in Desmos, is going to be, let's see, 7/2 y squared minus y is equal to 1/3 x cubed plus 3x plus c. Oh, well, c is going to be 43 plus 1 over 3. Okay. And I guess my solution is given by this red curve. Nice. I want to illustrate one thing to you, which is that if we, instead of supplying numbers 4 and 2, what if I just tell you instead that we're going to assign some initial value for y, which I'm going to call y0, and some initial value for x that I'm going to call x0. Then when we ask the question, what is c, instead of plugging in 4 and 2, we would write 7/2 times y0 squared minus y0, and then I'll subtract 1/3 x0 cubed, and then I will subtract 3x0, and that's going to be equal to my value c. Let me put that in Desmos. So I'll just replace that with a c, and then c is going to take on the values 7/2 y0 squared minus y0 minus 1/3 x0 cubed plus 3x0, minus 3x0. And then I'm going to add sliders for x and x0. And the last thing I like to do on Desmos is throw in an x0 comma y0 point, so that way I can grab this point and move it around. And I want to show you that the same differential equation has many, many, many solutions depending on these initial values that you give it for x and y. And so every time I move around this dot, it changes the initial value for x and y. Basically, the x-coordinate of this dot is the initial value for x, and the y-coordinate of this dot is the initial value for y. But you'll notice that the solution always exists, no matter where I move this around, right? Unless maybe, let me try something. Oh, no, that works too. Okay, so anyways, there you go. That's a neat thing to check out. If you have time. Okay, one more example and we'll be done. This says solve the following differential equation. This is just a little bit of extra practice. I encourage you to pause the video and try this one on your own, but then again, you do have some online homework where you'll be working plenty of these anyways. So notice y prime is just dy dx. Remember, the prime just means a derivative. And so this is going to be a situation where I want to multiply both the left and the right side by y squared plus y. So this is going to give me something like that. And then I'll take the antiderivative with respect to x, so I can cancel out that derivative and do the same thing to both sides here. So this is going to give me 1/3 y cubed plus 1/2 y squared is equal to 5/2 x squared plus c. And I'm going to leave this alone with the note that whatever initial values y naught and x naught I choose, c is going to be 1/3 y naught cube plus 1/2 y naught squared minus 5/2 x naught squared, and that's going to be the value for c. So if we plug this into Desmos, we can visualize all of the solutions that we'll get. Is 1/3 y cube plus 1/2 y squared equals 5/2 x squared plus c. And so we end up, again, c is equal to 1/3 y naught cube plus 1/2 y naught squared minus 5/2 x naught squared. It seems like this never really becomes that interesting, does it? It's not as pretty as the other one that we were messing around with. In any case, there's a little bit of interesting stuff going on. Let me rescale everything because I think I messed up my scale earlier. So we want x between like 0 and 10 and y between 0 and 10. Maybe that's going to be more interesting. Yeah, that is way more interesting. Okay, I'm glad I did that. I'm glad I fixed the scale. So again, dragging around this dot changes my initial values for x and y, and you can see I have different solutions to my differential equation depending on my choice there. In my actual example, I said let's let y equals 1 when x is equal to -1. So if I let y be 1, or y not be 1, and x not be -1, that's the particular solution that I'm looking for in this example 6. Okay, y'all have a great week.